In the final video for Lesson 2, Section 3, we will continue to use algebra tiles to solve linear equations, but we will be able to expand on their use by introducing the little surprise I mentioned in the previous video. Thus far, our algebra tiles have only represented positive values. So this is our positive variable tile, and we have our positive unit tile. As we continue our look at solving linear equations using algebra tiles, we will now be introduced to the negative unit tile. This is the surprise. We changed the color of the unit tile here to red to represent a negative unit tile, and one red unit tile represents -1. 3 red unit tiles would represent -3, and so on. And in case you're wondering, there does exist a negative variable tile, but we will not be using it in grade 7. We will save that one for next year. We also need to understand the idea of a zero pair. If we have one positive unit tile and one negative unit tile coming together, this will give us a zero pair. When you combine them, they result in 0. In other words, they cancel each other out. Just like a +1 plus a -1 would give you 0. Or 1 subtract 1 would give you 0. In certain situations, we will be using zero pairs to eliminate unit tiles in an equation in order to help us isolate the variable. Our first example, n subtract 3 equals 4. And just as a note, this is the same thing as saying n plus -3 equals 4. Both representations are the same. So if we're going to use algebra tiles, we're going to represent our n subtract 3 equals 4. To do that, we will need our one variable tile for the 1n. I have 3 red unit tiles for the -3 and 4 yellow positive tiles for the +4. So this would be our 1n. This is our -3 or -3 part, and this is our +4. If we are trying to isolate our variable tile, these 3 negative unit tiles, they pose a problem. We have to get rid of them. And here's where we run into a bit of trouble, because I can't just take 3 red unit tiles away from both sides. Why? Because I don't have any red unit tiles on the right-hand side. So I can't just remove them. This is where the idea of zero pairs come in. So to eliminate 3 negative unit tiles on the left, we must add in 3 positive unit tiles to create 3 zero pairs. So let's have a look. There's the original. We put in our 3 positive unit tiles, creating the 3 zero pairs. But if we just added in 3 positive unit tiles on the left-hand side, because of the preservation of equality, we have to do the same thing to the other side. So we pop in 3 positive unit tiles on the right. Now we can remove the 3 sets of zero pairs. Remember that each zero pair, they cancel each other out. They just give us nothing, so we will remove the 3 zeros. What are we left with? We have isolated our variable tile, which is exactly what we wanted. And on the right-hand side, we now have left 7 unit tiles. Therefore, n equals 7. We have solved the equation. Let's verify. N subtract 3, circle 4. In place of the n, we put the 7 that we just found. 7 subtract 3. We're trying to figure out if this equals 4. 7 subtract 3 is 4. And yes, 4 equals 4. N equals 7. Correct solution. Our second example, we have m plus 1 equals -5. Let's represent 1m, 1 unit, and then we have 5 negative unit tiles on the right-hand side. This corresponds to my 1M, 1 positive unit tile, 5 negative unit tiles. Left-hand side, right-hand side. In this example, to get our variable tile by itself, we have to deal with this positive 1 unit tile. We are unable to simply remove one from both sides because on the right-hand side, there are no positive unit tiles. What do we introduce? We have to introduce our 0 pair here. So to eliminate 1 positive unit tile on the left side, we create a 0 pair by adding in a negative unit tile on the left. There we go. Create the 0 pair. If I've added in a negative unit tile on the left, I must do the same thing on the right. The 0 pair now, we can get rid of that. And we have solved our equation. We now have our variable tile isolated, which is exactly what we want. On the left-hand side, we're left with our 1M, and on the right-hand side, we have 6 negative unit tiles, therefore, -6. M equals -6, and we will verify. I start with my equation, M plus 1. In place of the equals, I put a circle. We figured out that M is -6. Let's see if it works. -6 plus 1, -5. Yes, indeedy. -5 equals -5. M equals -6 is the correct solution. In our third example, we have -7 equals 1x subtract 2. Let's represent the left-hand side, 7 negative unit tiles, and on the right-hand side, 1 variable tile to represent the x, and then 2 unit tiles, 2 negative unit tiles for the -2. To get our variable tile by itself, to isolate it, we have to deal with the 2 negative unit tiles. This one, are 0 pairs necessary? I think not. We do not need to create 0 pairs. We can simply remove 2 negative unit tiles from both sides of our equation. So if we can get rid of them on both sides, let's do it. Here's the original 2 unit tiles that I'm going to remove. There they go. And yeah, we've isolated the variable tile, which is exactly what we want. So therefore, our variable x will equal 5 negative unit tiles, which means x equals -5. Let's verify. -7, x subtract 2. In place of the x, we found x to be -5. -5 subtract 2. Your work on integers comes into play here. -5 subtract 2 is indeed -7. -7 equals -7. X equals -5. Correct answer. If, by the way, in the process of verifying or checking, things don't work out and one side doesn't equal the other, chances are it's probably one of two things. Either you made an error in the verification, or you actually need to go back to where you solved the equation and have another look there. Hopefully, everything works out the first time. And now I'd like you to proceed to the activities for Lesson 2.